Swayam Prabha. Digital India. Educated India.
We are in week 2, and in the last class we have discussed the definition of a random variable, and then we have discussed the cumulative distribution function of the random variable, and we have given the one example for the CDF of the random variable also. We have given 5 different CDFs in a graphical way. Now, we are going to discuss the types of random variable based on the CDF of the random variable. If you recall that 5 different diagrams which we have made it for the CDF, out of those 5 different examples, we can classify those 5 examples into 3 types of random variable. First, we discuss the discrete type random variable, and the second we discuss a continuous type random variable, and third we discuss mixed type random variable. So, any random variable can be classified into any one of these 3 types of random variable, namely discrete type random variable, continuous type random variable, or mixed type random variable. So, in this class I am going to explain the types of random variable with the form of first the definition of the discrete type random variable, then continuous type random variable, then mixed type random variable, and followed by the definition I am going to give 1 or 2 examples for each type. So, that is the plan for today's lecture. So, let me start with the first type. So, it is called types of the random variable. Types of the random variables. The first definition is discrete type random variable. When we say the random variable is discrete type random variable, a random variable in short we will be keep writing RV. A random variable x is said to be a discrete type random variable if its CDF cumulative distribution function has countable number of discontinuities. The countable number of discontinuities means the discontinuities or jumps can be finite or countable infinite. That means a random variable is x is said to be a discrete type random variable if its CDF has a countable number of discontinuities or it has a countable number of jumps. Say the discontinuities or jumps as x1, x2 and so on. Initially I am writing countably infinite, it could be finite also. Then one can define the probability of x takes a value xi, that is nothing but P of collection of W such that x of w gives the value xi, where w is belonging to omega. So, this is for I is equal to 1, 2 and so on. You have a probability space omega f p, p is a probability measure. So, the probability of x equal to small x, that is nothing but a collection of possible outcomes gives the probability in which the x of w gives the value xi. So, you collect those possible outcomes which gives the values xi under the operation capital X. So, that is nothing but the event. So, find out the probability of event, that event is going nothing but the probability of x equal to xi. Therefore, when you write the CDF of the random variable x, I can go for suffix x or suffix, I can omit the suffix x, that means I am talking about the CDF of the random variable x, that is nothing but collection of all the p of x takes a value xi's such that all the xi's has to be less than or equal to small x. So, here x is between minus infinity to infinity. So, whenever you have a discrete type random variable, the CDF is nothing but a collection of adding p of x equal to xi's where xi's is less than or equal to small x. Here the xi's where I is equal to 1, 2 and so on, it could be finite or it could be countably infinite, are called the jump points. Why it is called the jump points? The CDF of this random variable has a jump only at these points, and the probability of x takes a value xi, that is nothing but the jump values. So, these jump values are strictly greater than 0. So, wherever the x equal to xi in which the p is equal to greater than 0, p of x equal to xi is greater than 0. So, these values are called the jump values. At those jump values, the CDF has a jump, and wherever there is a jump, and those points are called the jump points. That means the p is equal to p of x equal to xi for different x, it could be either 0 or greater than 0. If it is greater than 0, then those xi's are called the jump points, and the p of x equal to xi in which it is greater than 0, and those are called the jump values. Therefore, I can draw the CDF of in general CDF of a discrete type random variable as suppose x1 is here, then the CDF is 0 till x1. At the point x1 there is a jump. So, that height is a p of x equal to x1, that is a jump value, and this x1 is a jump point. Till the next point x2, the value is same, and the CDF has a jump at the point x2. Suppose at x2 the next jump is some value. So, p of x equal to x2 there is a jump. So, this difference height, that is a jump value. Till x3 it has the same value, then there is a next jump. Like that it may keep going, and you know that it is a CDF, therefore, it always start from 0, it will end up 1, and this CDF has only jumps, that is very important. Then only it is going to be called it as a discrete type random variable, and the other points the values is 0. I can equivalently draw the another diagram for p of x equal to xi. That means at point x1 it has some height, and x2 it has another height, and x3 it has another height. Suppose this height need not be same, it can be a different values. So, these heights are nothing but the jump values, and these are all the jump points. Like that I may have many more. So, whenever you have a CDF of some random variable which has only jumps, the jumps could be finite or countably infinite, then that random variable is called it as a discrete type random variable. The way I have written P is equal to P of x equal to xi, which has the jump values and jump points, I can create another, I can define another function that is called a probability mass function. The probability mass function, in short it is PMF, the probability mass function of the discrete type random variable as the probability mass function of a discrete type random variable is defined as P of x is nothing but the probability of x takes a value xi. This P of x is called the probability mass function. So, this is defined for all x belonging to R real line. It has the following properties. The first property, since we made a P of x is a probability of x takes a value xi, probability of x equal to xi. So, wherever there is a probability of x equal to xi, it is this much, otherwise it is 0. This is the way the P of x is defined. It has the property, the P of x is always going to be greater than or equal to 0 for all x. That means wherever there is a jump value, that value is going to be strictly greater than 0. Wherever there is no jump, that means the P of x is going to be 0. The second property, if you add all the values of a P of x equal to xi, you will get P of x summation will be 1. Always the probability mass function satisfies these two properties. It is greater than or equal to 0, and the summation over x it is going to be 1. So, if you have a discrete type random variable, it has a probability mass function satisfies these two conditions or these two properties. If any real valued function satisfying these two properties, then one can say this is the probability mass function of some discrete type random variable. So, any probability mass any discrete type random variable has a probability mass function satisfying these two properties, or any real valued function satisfying these two properties is the probability mass function of some discrete type random variable. I will go for one easy example which we have discussed earlier in the form of CDF. Recall, there is a one problem in which the random variable x is number of heads obtained for the random experiment of tossing two unbiased coins. When you toss a two unbiased coin, and if you define the random variable x is a number of heads obtained, then the f of x is 0 till x is less than 0. It is 1 by 4 from 0 to 1. 3 by 4 it is from 1 to 2, and the values is going to be 1 from 2 to infinity. So, this is the example we have discussed in the CDF for the random variable. Now, we are discussing the same example. If you draw the CDF of this random variable CDF capital F of x. So, till 0 it is 0, 0 there is a jump of 1 by 4. At the point 1 there is a next jump, it is 3 by 4. The value at the point 1 is 3 by 4. So, the jump value is 3 by 4 minus 1 by 4. So, 1 by 2. At the point 2 there is another jump of 1 by 4. So, it will be 1 from 2 onwards. Therefore, the P of x is at x is equal to 0, it is 1 by 4. At x is equal to 1, 1 by 2. At x is equal to 2, it is 1 by 4. And all other point it is 0 all other points. So, I write otherwise. So, when we write otherwise, that means the probability mass function value is 0 at it is 1 by 4 at 0, 1 by 2 at 1 and 1 by 4 at 2, and all other points it is 0. So, I can draw the probability mass function also. So, at 0 there is a height of 1 by 4, and at x is equal to 1 at height of 1 by 2, and at x is equal to 2 there is another height 1 by 4, and all other points it is 0. And if you add all the jumps, the jump values 1 by 4 plus 1 by 2 plus 1 by 4, that is 1, that is the second property, and all the values are greater than or equal to 0. That means at only these 3 jump points it has the jump values, and all other places the values are 0. Therefore, this is the probability mass function of the discrete type random variable. Why it is called a discrete? Because you see the CDF has only jumps, and the jump points are 0, 1 and 2, and the jump values are 1 by 4, 1 by 2 and 1 by 4. Since the CDF has discontinuities, therefore, this random variable, that is a number of hits obtained, this random variable capital X, that is a discrete type random variable. And the probability mass function of this random variable x is P of x, that is 1 by 4 at x equal to 0, 1 by 2 at x equal to 1 and x equal to 2, 1 by 4, otherwise it is 0. Since it has 3 jump points and 3 jump values, therefore, I am just writing the probability mass function this way and 0 otherwise. There is a possibility in general you may have a CDF has a finite number of jumps or countably infinite number of jumps, and one can find out what is the probability mass function of that discrete type random variable also. So, this is a very easiest example in which we can represent the CDF first. By seeing the CDF, we can conclude it is a discrete type random variable, and from the CDF you can get the probability mass function by subtracting, because the CDF is nothing but the summation of probability mass till that point. So, from the CDF one can get the probability mass function, or from the probability mass function one can get the CDF of a discrete type random variable. Now, we will move into the second type of random variable, that is a continuous type random variable. Continuous type random variable. When we say the given random variable is of continuous type, a random variable x is said to be a continuous type random variable if its CDF is a continuous function in x. That means whenever the CDF of a random variable is a continuous function in x in the whole range from minus infinity to plus infinity, that means there is no discontinuity in the CDF of the random variable, then you can conclude it is a continuous type. For a discrete type random variable, it has a finite or countably infinite discontinuities, but for a continuous type random variable, the CDF is a continuous function in the whole range from minus infinity to infinity. That means if you draw the CDF without lifting a pen or pencil, you draw the CDF, then that is a continuous type random variable CDF. Since it is a continuous function, one can write the continuous function, left hand side is a continuous function, in the form of minus infinity to some x, some integrand dt. This is possible whenever the function is a continuous function in the whole interval minus infinity to infinity. Here x is from minus infinity to plus infinity, because of the CDF is a continuous function, where the small f of t, okay, till now we are using the capital F of capital F, now I am start using small f, where small f of t, that is called the probability density function of the continuous type random variable capital X. This is possible whenever the CDF is a continuous function. So, whenever the CDF is a continuous function, we call that random variable as a continuous type random variable. The integrand in this equation, that integrand is called the probability density function. The way the probability mass function satisfies a few properties, the two properties, similarly one can identify what are all the properties going to be satisfied by this probability density function of the discrete type random variable. So, it satisfies the following properties. That means the probability density function satisfies the following properties. You know that the CDF values is lies between 0 to 1. It starts from 0, it will end up 1, and monotonically increasing, continuous or right continuous function. Therefore, the integrand always greater than or equal to 0 for all t. Not only that, since you are writing capital F of x as the capital F of x as the minus infinity to x of integration f of t dt. So, if you go for limit x tends to infinity, you know that limit x tends to infinity of capital F of x is 1. From there you can get the second property, that is minus infinity to infinity f of t dt, that is 1. That means a real valued function satisfying these two properties will be the probability density function of some continuous type random variable. If you have a continuous type random variable whose CDF is a continuous function in the whole real line minus infinity to infinity, therefore you will get the probability density function. So, we can relate, suppose you know the CDF, you can get the probability density function. I am writing f of x, either f of t or f of x, does not matter, by differentiating the CDF with respect to x, you will get the probability density function. From the CDF you can get the probability density function, from the probability density function you can get the CDF. We are going to do some example through that, we will explain in detail also. I am going for 2 examples, through that I am going to explain this continuous type random variable. The first example, let us consider the example 1. Let x be a random variable with the CDF given by capital F x that takes a value 0 till 0 and it takes a value x between 0 to 1 and it takes a value 1 from 1 onwards. You can draw the CDF, it is a rough diagram. CDF is 0 till 0, from 0 onwards it is x and at the point 1 onwards it becomes 1. By seeing the CDF, you can conclude this is a continuous function from minus infinity to plus infinity, continuous function in x. Therefore, this is a continuous type random variable. Therefore, x is a continuous type random variable. You can find out what is a probability density function of this continuous type random variable by differentiating the CDF. So, if you do the differentiation of CDF, you will get 0 when x is less than 0, similarly x is greater than 1. And if you differentiate x, you will get 1 between the interval 0 to 1. That means the probability density function of this continuous type random variable, the value is 1 between the interval 0 to 1 and otherwise it is 0. That means you can draw this rough diagram, the probability density function, it is a small f of x. The capital F of x is the CDF, small f of x is the PDF. So, in short it is a PDF. So, the value is between 0 to 1, the height is 1, otherwise it is 0, therefore no need to. So, the horizontal line 0 to 1, the height 1, that is the probability density function of this continuous type random variable. I will go for one more example. Example 2. Let x be a continuous type random variable with PDF given by small f of x, it takes a value e power minus x between 0 to infinity, 0 otherwise. Whenever we say 0 otherwise or elsewhere, some books they use the word elsewhere, that means the probability density function which is a positive value between the interval 0 to infinity is e power minus x, and the remaining intervals it is a 0. So, here the remaining interval is a minus infinity to infinity. So, you can draw the probability density function. So, e power minus x, so it takes a value, it is going down, asymptotically touches 0 at infinity, and at 0, so the f of x value is 0 till 0. From the probability density function you can get the CDF by integrating minus infinity to till that point of probability density function. So, since the probability density function is 0 from minus infinity to infinity, you can say it is 0 from minus infinity to 0. From 0 to infinity you have to integrate and find out. So, if you do the simple integration, you will get 1 minus e power minus x between the interval 0 to infinity. You can include 0 also. So, you can make it 1 minute. So, minus infinity till 0, and 0 onwards it is 1 minus e power minus x. You can draw the CDF of this continuous type random variable. So, till 0 it is 0, and 0 to infinity it increases, it touches 1 at infinity. This is a CDF of a this is a CDF of a continuous type random variable. So, from the CDF you can always get the probability density function of a continuous type random variable. From the probability density function one can get the CDF of the continuous type random variable.